And welcome back, Algebra 1 students. More material in Chapter 7 over exponents. Section 7.5 is about radicals and their connection to a fractional exponent. And so let's jump right in. Whenever you have an exponential expression and the exponent is a fraction, it is possible to rewrite this as a radical. And so what you see here is the denominator in the fractional exponent becomes the index, we call it, of the radical, and the numerator of the fractional exponent comes into one of two places. You have choices. You can put it inside the radical and put it on the variable, or you can put it outside in the set of parentheses. So there's a little bit of lingo here to keep this straight, so I'm going to move on to here. And so here's basically how this works. Whenever you've had a fractional exponent, or whenever you've had a radical, I should say, the relationship is, if you never have known, the index of the radical is that little number here that's telling you what the value here of the radical is. Is it a square root, a cube root, a fifth root? Well, that number goes here. Now, weirdly, in the world of math, this is one of the only times when a number 2 is implied and not written. So your whole math life, if you've been writing square roots, you never put a little 2 there, but it was actually implied to be there. Well, that will now be, that's the connection to the denominator of the fractional exponent. So the index of the radical is the denominator. The numerator of the fractional exponent goes inside the radical here, the radical symbol, and whatever's inside the radical, we call that the radicand. And we place that normally here. Now, this is what we do most of the time. This additional option up here is a little bit more rare, but it does come in handy, and we'll look at some examples. But you want to be really fluent with this and going back and forth. So in this section, half the problems are taking the fractional exponent and rewriting it as a radical, and the other half of the problems are, given it as a radical, rewrite it with a fractional exponent. So let's just see what they look like, and we'll practice a few. So right here, whenever you see 5 to the 1/2, then, that actually is the equivalent statement of the square root of 5. Now, the square root of 5 is not a perfect square. We would just leave it like this. You should know it's a little bit more than 2, but you can see that the denominator of 2 is the index of the radical, but we don't write it, because when the index is 2, we rarely write it. In this textbook, though, you will see it a fair amount in this chapter. Now, the numerator being 1, that's 1 we don't write. So this is kind of a unique question. There's 2 values from the fractional exponent that are not written in the radical expression because they're implied. It can always be confusing when terms are implied versus explicitly written. So we could tweak this very quickly, and we could say, well, I'm going to actually put a 2 there and a 1 there. That'd be more complete. All right, so let's look at some examples over here. So x to the 1/3. Now, that's one where the denominator being a 3, we are going to write that because this is the cube root of x. But the 1 being the numerator, we wouldn't write that over there. So that's another way to write the x to the 1/3. Now, how about m to the 2/3, another variable? Well, once again, you can see the index of the radical and the denominator match, and then the numerator became inside the radicand here on the variable. Another example right here has an extra step we have to consider. So now what winds up happening the deeper you go into Chapter 7 is all of these rules and all of these issues from Section 7.1, 2, 3, and 4, and also prior knowledge, really starts to become important. Because now we have a set of parentheses here, and this fractional exponent is speaking to the entire term. It's not just talking to the a. So that means the entire 5a is going to be my radicand. My 4 went to my index, and my 3 went out front. Now, the reason there's an asterisk here is because you have to be careful. Sometimes what is desired is to expand, if you can, what's inside here. Well, this 3, using your rules about an exponent outside of a set of parentheses, you could bring this in, and you could actually do this. You could say, well, would this be the same as the 4th root of 5 cubed, a cubed? And that is true. And then could you simplify 5 cubed? That's a cube that you should know. 5 times 5 is 25. Times 5 is 125. So this actually could be written as 125a cubed. And that would be the simplified version. The last thing on this board, you want to make sure, and this has to do with this last question here, is there a difference between when the fractional exponent is outside of a set of parentheses versus just on a variable? So again, this overlaps with some prior knowledge that we learned, that the 1/2 is speaking to everything here. Here the 1/2 is only speaking to the x. So these would be set up a little bit differently. Since this is speaking to the entire thing, I'm going to write vertically here, and I'm going to go ahead and write 2 as my index here. That means this entire thing would go inside. My radicand is 25x, and my numerator being 1, I don't need to write it anywhere. That would be the fractional expression, or the radical expression of this fractional exponent. Now this one, the 1/2 is only talking to the x. The 25 is just sitting there. So I don't do anything to the 25, but I am going to write this as 25 rad x. So again, prior rules, you just want to be careful. Well, let's look at what happens now. So these examples here were going to fractional exponents, and we were writing them as radicals. Well, now let's go the other direction. So here on my other board, I want to go from radicals to writing them as fractions. So let's take a look here. Now I just jumped in with this one, and I said, well, what if we had the cube root of w squared? Well, just like before, my radicand now becomes the base of my exponential. My index, that number 3, goes over here to become my denominator, and my exponent in the radicand becomes my numerator. So now we're going the other way. All right, so let's jump to this example here, and we've got quite a bit going on here. There's no value written here, so there's a 2 implied. So I'm going to go ahead and write that. I'm going to say, well, I guess there's a 2 right there. And what I could say is, well, it kind of looks like it's going to be 7a cubed b. And this entire thing is going to be raised to the, well, there's a 2 from my index. That's my denominator. And inside here, there's just a 1 on everything. So it would be the square root of that entire term. Now, what you can do is take this a second step. And you could say, well, could I bring in the 1/2 onto each one of these? And you could. And you could say, well, this is 7 to the 1/2. This would be a to the 3/2, and this would be b to the 1/2. That would be acceptable. So oftentimes the instructions need to be really clear about how far you want to go. All right, now let's look at 50x. We need to write this. Well, I'm going to put stop right here for review because I want to go over a concept that is supposed to be a skill that you have, but you may not. It's about reducing numbers inside a radical. So I'm going to do a brief timeout here, and I want to review a concept from the past. It has to do with simplifying radicals. Now, sometimes heading into Algebra 1, I find this is one of those topics that about half the class has done a lot of it, and half the class has done very little to none. So I just want to explain how this works. So I have 2 examples here. I have the square root of 75. I wrote them twice because I'm going to do it 2 different ways. There's 2 approaches to these. And cube root of 80. So the way to simplify a radical, the one way is to do a prime factorization, or a factor tree. And the other way is to find perfect squares, or it could be perfect cubes, or whatever the index of the radical is. So I just want to go to prime factorization. Most students are good with this. And you just take a number and you do your factor tree until you get to primes. So what I'm going to do here with root 75 is I'm going to say, well, let's see, 75. I think that is 25 times 3. 3 is prime. And 25 is 5 times 5. So it looks like my prime factorization is the following. So I'm going to rewrite this like so. I'm going to say, well, it's 5 times 3. So I'm going to take the prime factorization and put that and rewrite the number like so. I'm also going to very intentionally put my index on this one. Okay. Now, here is what it means when you reduce a radical. The index is a very important number. If there is a number after your prime factorization that occurs the same number of times as the index, then you're allowed to take it out of the radical. So, since the index is 2, that tells me if any factor occurs 2 times, it can be removed from the radical and placed out front. So I see the square root of 5 times 5 times 3. I very quickly notice, I'm like, well, 5 times 5. I have 2 5s. That means I'm allowed to take them out. Now, when I take them out, I only represent it with 1 5 because I'm outside the radical now. And I would say, oh, well, this is now going to be 5 times the square root of 3. Now, 3 only occurred 1 time, so I'm done. I just simplified square root of 75 to 5 rad 3. All right? Now, that's one way to do them. Now, some students weren't taught that way. Some students were taught this other way, to find perfect squares. Now, the only disadvantage of doing perfect squares is you have to know your perfect squares really well. So what I'm going to do on this one, and I picked some kind of easier questions here. Square root of 75, a lot of students would look at that and say, oh, well, I know the square root of 75. That's 25 times 3. And 25 is a perfect square. So remember, it says find perfect square factors. Well, since 25 is a perfect square, the square root of 25 is 5. That's going to allow me to take that out in front. And I would say, oh, well, that's 5 rad 3. Notice I got the same answer either way. Now, there's advantages to both of these. If you're doing square roots, a lot of students like this method because it goes pretty quick. But as the index of the radical increases, this is a difficult strategy because a lot of students don't know all their perfect cubes or their perfect fourth values raised to the fourth or fifth power, depending on what you have to reduce. So I'm going to do another example. I'm going to use the square root of 20 as a nice one. So let's do a square root of 20 this way, and we'll do it this way. So let's see if I sneak this one in right here. So how about the square root of 20? Well, the square root of 20, you would break that one down into 2 times 10, and then 10 is also 2 times 5. So I'd say, okay, well, this is equal to 2 times 2 times 5. And since my index is 2, if something occurs twice, I can take it out front. So I've got 2 2's. I can take one out. This would be 2 rad 5. If I did it this way, I would say, okay, the square root of 20. Well, the square root of 20 is 4 times 5. 4 is a perfect square. The square root of 4 is 2, and that would be 2 rad 5. Again, same answer either way. Now I'm going to do this same question here with the cube root of 80. Now the cube root of 80, I'm going to do it the factor tree method, and I would look at this and say, well, that's 8 times 10. And then 8 is 4 times 2, and 4 is 2 times 2. And 10 back here is 2 times 5. Okay, and now as I look at this, my prime factorization, I've got 1, 2, 3, 4, 5, 4 2's and a 5. So I'm going to go up here and say this is equal to the cube root of 2 times 2 times 2 times 2 times 5. Now if you want, you could write this as 2 to the 4th. That works too. But I'm going to look at this. I'm going to say, well, if something occurs 3 times, I can take it out. Well, look at 2 is occurring 4 times. But I'm going to look at these 3, and I'm going to take it out front, and I'm going to say, oh, well, this is 2 times the cube root of 10, because there's a 2 and a 5 left over. That would be my simplified version. Now, as I look over here, what if I would have done this with perfect cubes? Well, the downside of this is I need to know how to do perfect cubes. Well, perfect cubes, for this one, I would say, well, 8 is a perfect cube, so that's kind of jumping out at me. And I would say, oh, well, this is equal to the cube root of 8 times 10. I know that the cube root of 8 is 2. I would take that out front, and I would say 2 cube root of 10. And again, notice you get the same answer either way. Okay, I'm hoping that that comes back to you for those of you guys that did this before. And if you haven't, that makes sense how this works. And we'll practice more of those in class. With that quick review, I want to come back to this question. This is why I stopped here for for the square root of 50x. If you look at the square root of 50x, and you go to write that with a fractional exponent, you might hesitate and go, well, wait a second, I think I can simplify 50. And you'd say, well, isn't this actually the same as the square root of 25 times 2 times x? And you'd say, should I rewrite this as 5 rad 2x and then write my answer? And the answer is, sure, you could do that. Or you could have jumped right to here. So I'm going to do this both ways. So let's say you just looked at this and you said, okay, it looks like it's going to be 50x, and it's going to be raised to the 1/2 power. And then you said, I'm going to bring the 1/2 onto here, and I'm going to say, oh, well, this is 50 to the 1/2, x to the 1/2. Well, what's expected is that you know that you're perfect. You know that these are reducible. So you always want to check to see if it's reducible. If it's easier for you to do that here, you could say, wait, the square root of 50, that turns into 5 rad 2. And from here you would say, oh, that's 5 rad 2, but that's going to be 5 times 2 to the 1/2, or I'll actually put in an intermediate step. You would say, well, this is going to be 5 rad 2 times x to the 1/2, but I'm going to write that with a fractional exponent. And you would say, well, that's going to be 5 times 2 to the 1/2 x to the 1/2. Or you could do this from this step after reducing it, and you could say, well, would this be 5 times 2x to the 1/2? Both of these are equivalent statements right here. Okay. Let's jump over to here. Cube root of 24a squared. You might notice right away 8 comes up all the time. And so you look at this and you say, oh, wait a second. This is going to be the cube root of 8 times 3, that's 24, and then I've got a squared. You might say, wait a second, cube root of 8 is 2. I'm going to make this a little easier on myself, and now I'm looking at this. Now again, you could have done this like I showed on the other board, and you could have written this out in the factor tree and had 3 2's and taken it out. I just happened to know, I like doing the cube root of 8 and took that out. So now here I would say, all right, I've got the 2 out front, and I'm now going to say I've got 3a squared to the 1/3. Then I can bring that in, and I can say this is 2 times 3 to the 1/3, a to the 2/3. Okay. All right, how about this one, 72? Now 72 you might not notice right away. It's even, so you say, well, maybe this one I'm going to do the factor tree way. 2 goes in there, and then 2 goes into 7 3 times, and then that's the remainder. 1 goes into 12 6 times. 2 times 36, you might go, oh wait, 36, that's a perfect square. You'd say, wait a second, I think maybe I can do this one. This is the square root of 2 times 36 times m to the 4th. You'd say, I'm going to take the 6 out. So now I'm looking at 6 rad 2m to the 4th. Now it's time for the fractional exponent work. This will be 6 times 2m to the 4th to the 1/2. 6 times 2 to the 1/2 times m to the 4/2. Then you go, wait a second, should I reduce that to 2? And yep, you should. And you can say, oh, I guess that's going to be m squared. Okay. Then our last one here, 54. Maybe you don't recognize that one either, but you just say, well, I'm just going to try to divide this one by 2. And 2 times 27 is what it turns out to be. But 27 is a perfect cube for 3. And so you'd see this one, you'd say, oh, this is going to be the cube root of 2 times 27 times y to the 7th. Cube root of 27 is 3. And then you'd say, well, this is 3 times 2y to the 7th to the 1/3. And then you'll bring the 1/3 in. You'd say, well, this is 3 times 2 to the 1/3 y to the 7/3. Okay. And that's what it would look like. Now, obviously, these over here are much more complicated than these simple ones here. And usually we try to keep things more simple in Algebra 1, but they start to get more complex, and there's more issues that come up with absolute value and even exponents, even indexes. They're more sophisticated things that we deal with later. But mainly you just want to be comfortable going back and forth, and we tend to try to keep them more on the simple level. All right, so that's radicals to fractional exponents and fractional exponents to radicals. All right, so that is 7.5. So good luck with homework there, and we will see you next time.